using the impedances that we talked about in the previous days. Okay, it was yesterday. So let's get going. Usual should be 1143. Sorry. E1143, which is our electrical engineering circuit analysis, and we are now going to our AC circuit analysis. Now, before we go any further, let me point out that AC circuit analysis and the DC circuit analysis, in terms of the method and the approach, they are basically the same, right? However, you will notice that when we are dealing with AC circuits, we are dealing with an impedance which can have a component in the real axis and a component in the imaginary axis, if you remember your complex numbers. So you realize that I will just dwell much on how we do calculations using those complex numbers, and I will not focus much on the methods, because Ohm's law is still Ohm's law, whether it's AC or DC. Kirchhoff's law is still Kirchhoff's law, whether it's AC or DC. A star-delta connection is still a star-delta connection, whether it's AC or DC. So what I'm saying is, after dealing with these components, all the other methods of circuit analysis can be applied, right? So how do you apply that? We said the opposition to AC is what we term as impedance, right? So when I'm talking about impedance, in reality, I'm just talking about if it was DC, it is resistance as such. But now, why do we talk about impedance? It's because of those components, the imaginary component and the real component. Okay, that is the one which differentiates between AC and DC. But once that is clear to you, you realize that you can now analyze any circuit. When I say any, I mean any electrical circuit, by putting to use the theories, the theorems, the laws that we talked about when we're doing DC circuit analysis. Okay. Now, what's the difference? R plus J, let's say R plus JXL, will be R in that direction plus XL in that direction, such that their result, right, the result of that will be this. Okay, so this becomes your Z. So as you can see, it's like vector addition. Okay, you are adding two vectors together. Okay, that is the only difference. However, when you're talking about R plus R, it was straight away to R. But when there is a complex component, the plus J is going up, the minus J is going down, right? So this is minus JXC. So if we look at that in terms of the components, you realize that for XL and XC, you can easily add and subtract, right? Because they are on the same axis, right? On the imaginary axis. But you can not do straight away addition when it becomes R and X something, right? So I'm taking that slowly so that we understand what I'm talking about. That is basically the whole thing in this kind of scenario. So when you are given a resistance, it means the resistance is always in the real axis. That's why the angle is equal to 0 degrees. It's always on the real axis. Then the inductive reactance, which we said, let's say it's now our ZL, will be XL at an angle of 90 degrees, right? That is, it's going upward. That's why it's plus JXL. So this is the polar representation. This is the rectangular representation. Okay? Polar, rectangular. Capacitive reactance, ZC, becomes equal to XC at an angle of minus 90 degrees because it's going downwards. So this is the polar representation, and minus JXC becomes the rectangular representation. This is the most basic thing that you have to understand, that if you have capacitive reactance, then you know that it's going down. Inductive reactance, it's going what? It's going up. Okay? Then resistances are always on the real axis. Then we also talk about admittance and susceptance. Okay? So admittance is the inverse of resistance. So Y becomes equal to 1 over R, still at an angle of 0 degrees, which is equal to G. Remember, this becomes admittance, which was conductance in terms of our DC circuits. We are saying it's now admittance, right? That becomes G plus J0 because it doesn't have a complex component. Okay? Then inductive susceptance, right? Inductive susceptance is now the inverse of reactance. So it's 1 over XL, and it will be at an angle of minus 90 because it's the inverse of that. That's 1 over that. Then capacitive susceptance becomes 1 over XC. It's now at an angle of 90 degrees because it's the inverse of capacitive reactance. Okay, so that is basically what we are looking at in this kind of situation. Inductance and capacitance, their susceptance becomes the inverse of their reactance. Okay, that is what we have in terms of capacitors and inductors. However, you realize that we will rarely use the admittance and susceptances in our calculations. But if you find it simple, just like we're talking about conductances and resistances, you can still use that. And you still get the same results as N1, we have used reactance and resistance. So we can also apply Kirchhoff's voltage law to phasors. Sum of phasor voltages equal to 0 for any closed loop. We can also apply Kirchhoff's current law on nodes. Sum of phasor currents entering a node must equal the sum of phasor currents leaving a node. So, like I said, after you understand that you are just dealing with complex numbers and nothing more, you also realize that there is nothing quite different from the analysis that we did with our DC circuits. So how do we deal with the analysis of circuit using these phasors and impedances? So let's say you are given an equation of the voltage or the current. Remember, we said it can be Vm sine omega t plus whatever, right? Vm sine omega t maybe plus whatever angle is there, maybe phi or whatever, right? So replace the time description of the voltage and current sources with corresponding phasors. All of the sources must have the same frequency. This is very important. If you find 200T and the 250T, you cannot add this because they are not in the same frequency. That is very, very important to take note of. So you need the same frequency for you to be able to convert them to phasors and still be able to do your calculations. So replace inductances by their complex impedances. XL is called J omega L. That means if you have something in Henries, then you multiply by omega and the Henries so that you get your XL. Your XL becomes your complex impedance. Capacitance XC 1 over J omega C. If a certain capacitance in farads, then 1 over omega times C gives you your XC. Only resistances retain their values when you are dealing with these kinds of calculation. Only the resistors retain their value. So everything else changes. But again, you should note that these changes are only done when on the inductor, the unit is Henries, and when on the capacitor, the unit is the farad. Very important. Okay. Why do I say so? Because if you are given ohms on an inductor, it means you are already given the value of the complex what? Impedance. Take note of that. When you are given a value in ohms, then it means what you are given is the complex impedance for that component. Okay? It will be the complex impedance of that component. Right. Then you analyze the circuit using any of the techniques that we studied performing calculations with arithmetic, complex arithmetic. So what I'm saying is in AC, you are dealing with vectors, which have magnitude and in the direction. So the same way you add your vectors is the same way you add your impedances. The same way you add your vectors is the same way you add your impedances. I think that is clear. So I'm repeating that because that's the most important thing when you're dealing with this. So you should not worry yourself that we've not done maybe you didn't do Kirchoff's current law or whatever. You did Kirchoff's current law. So now all you need is to apply it bearing in mind that you are dealing with complex numbers. Okay, so let's go to an example. Calculate the total current and voltage across each element. Calculate current and voltage across each element. So we are given that the voltage Vs is equal to root 2 100 sine 500t plus 30 degrees. Okay. Then we remember our usual way, Vt is equal to Vm sine omega t plus 5 rho theta. Let's say plus 5. Then you go back and look at this. So in this case, you are given root 2 times 100 sine 500t plus 30 degrees. Okay. So we are saying you now want to replace this mathematical or time domain expression with the impedance. So with the phasor representation. So we take note of the fact that when you are given this expression, it means your Vm is equal to root 2 times what? Times 100. But on the phasor, we want to use the RMS of the voltage. That is what you put on the phasor. So what is VRMS in general? It is equal to Vm over root. VRMS is Vm over root 2. Okay? So our Vm is now root 2 times 100. So root 2 cancels out. That's why we have 100 here. Right? Then our omega, we have 500t with omega t. So it means our omega is called what? 500 from that expression. And our angle theta is equal to plus 30 degrees. Okay. So your Vs is now 180 at an angle of 30 degrees. Resistor, the resistance remains as it is. That's why our R is equal to 100 ohms. Then for the inductance, we need XL. So XL is equal to omega L. That means it's now 500 times 0.3. And we get our 150. It's a plus J because we said XL is on the positive imaginary axis. Right? Then XC, we have C in microfarads, that is 40 times 10 to the power minus 6 farads. And then we multiply 1 over 500, which is our omega, times 40 times 10 to the power of minus 6, and you get your 50. It's now a minus J because XC is on the negative imaginary axis. So this is now the circuit which you have to analyze. With the impedance is now given in the proper values. Okay. Let me remove what I was writing here so that we can see what follows. So I'm explaining this very slowly because that's the most important thing for you to know. After that, you realize that there's nothing difficult with the AC circuits. Besides the fact that the calculations now involve complex arithmetic. That's the only thing which will make these calculations not difficult but long, because it will take you time to resolve some of these things. They need proper attention. But if you have a calculator which you can convert between complex numbers and the like, it will be very fast for you to see. So the main difference with the DC circuits now is when you are given the mathematical expression in the time domain, then you have to convert it to the phasor by giving the RMS value of the quantity. It could be current, it could be voltage. You use the RMS value. So that means whatever magnitude you are given, it is divided by √2 to get what you want to get. Okay, so let's go. We said calculate the total current and voltage across each element. Just like in DC, when you want to calculate the total current, the first thing that you have to do is to calculate what? The total resistance. So in this case, also want to calculate the total impedance. Okay? These components are in series as usual. So you realize that Z total will be equal to Z across R plus Z across L plus Z C, right? So we have 100 plus J, because inductance and capacitance are in the same plane. Because capacitance and inductance are in the same plane, we can subtract them. So 150 minus J50, that means the overall effect will be 100 going upwards. So it's plus J100. This is the rectangular notation. Then you can now use your Pythagoras theorem to get this. Remember, we have 100 and 100. So this will be our resultant, R, this squared plus this squared or whatever. Then the angle will be the inverse tangent of this J, XC over XL, right? That becomes your angle. And like I said, there are calculators which can quickly convert from between these two, from rectangular to polar coordinates. You just check yours and see how it works. Then the current, we use Ohm's law. Current is called voltage over resistance. So here it will be voltage over the total impedance, right? So it's now 100 at an angle of 30 over 141.4 at an angle of 145. So we divide the magnitudes as usual, right? Then for the angles, is the numerator angle minus the denominator angle. So here it will now become 30 minus 45. That's why we have a minus 15 degrees, because it's the numerator angle minus the denominator angle when you are dividing these phasors, right? Then you get your 0.707 amperes at minus 15 degrees. So now we know this current is 0.07. Then the voltage drop across each component, just like in our normal Ohm's law, it is still equal to I times Z. right? The current times the impedance of that component. So across R, it will be 100 times I, right? Which is 70.7 at an angle of minus 15 degrees, right? Then in the time domain, it's now 70.7 root 2. We are going back to Vm, right? Sine 500t, that's our omega, minus 15 because our angle is 15 degrees. Okay? VL, that's J150 times that. J150 is 150 at an angle of 90 times 0.707. Now, this is for division, right? For multiplication now, the resultant angle is the sum of the two angles. In multiplication, you just sum up the angles straight away. The algebraic sum of the two will give you the resultant angle when you are multiplying. When you are dividing, you subtract the denominator angle from the numerator angle. So, VL becomes 106.05 at 75 degrees. In time domain, 106.05 root 2 sine 500t plus 75. Then across C minus J150I minus J means 50 at an angle of minus 90 degrees times that in an angle of minus 15. Then this we multiply them straight away, get 35.35 at an angle of minus 90 minus 15, you get minus 105, right? In time domain, magnitude times root 2 sine of 500t minus 105. I think I've covered basically everything that you need when you're dealing with these components in AC, right? So now if you were to draw the phasors now, your reference point, this is the 0 degree point, right? VS is at 30 degrees, you just draw it at 30 degrees and you put the magnitude, that's VS. VL, it is 75 degrees and its magnitude 106.1. VR is at minus 15 degrees, so it's going back there, right? Then you get its value. Then VC, as you can see, VC is directly opposite VL because they are in the same plane. Then the angle, that's this is what? 90 minus 75, that's 15, right? So this will be 15 plus what? Plus 90, that's minus 105. That's the angle of VC there. So that becomes the phasor representation of the quantities in that example. That becomes the phasor representation of the quantities in our example. Okay. Another example, so we've done the series components of it. On the series parallel, still the rules apply. Root 210 sine 1000t minus 90 degrees. So our magnitude becomes over root 2 to give us 10 here. Angle is still at minus that. So from the expression, we deduce that our omega is about 1000. That is what you just have to be able to extract from the given expression. Then after that, your L 0.1 means 1000 times 0.1, you get your 100 there, it's J. R comes back as R. C, XC becomes 1 over omega C. 1 over that, you get your 100 there. Now, how do you now go from there? We now have our ZR here. We now have our ZC. We now have our ZL. It's now a series parallel combination. What do we know about series parallel combination? Resolve components in series. Once they are done, go check for components in parallel. If you get them, resolve. and so on and so on. Okay, that is exactly what we will do. So ZRC will now be ZR in parallel with ZC. So what is ZRC? If there were resistances, product over sum. So still we have ZR times ZC over ZR plus ZC. The usual thing that we do, that becomes our ZRC. Then the total impedance becomes what? This plus that, because they are now in series. And we have resolved that. So what is ZRC? Product over sum. Right? And you get your value. First, we want to find the XC. Right? We know it's 100 there. So it's now 1 over R plus 1 over XC. Right? That's J 0.01. So now we have 1 over 0.01 plus J 0.01. To make things easy, you convert these two to polar coordinates. So realize that it's easy to add and subtract rectangular, right? And it's easier to multiply and divide in polar. So multiply and division, you better use polar. Addition and subtraction, you use rectangular. You should be flexible to move between those two forms. Okay? You should be able to move between those two forms. Rectangular to polar, polar to rectangular, depending on what you want to do. So since this is division, it is easier to convert to polar, do your usual division, then 0 minus 45, you get your angle straight away like that. That becomes your ZRC. Then, voltage across the capacitor, bear in mind that the capacitor now is part of ZRC. It means the voltage across these 2 points is still the same. So you can still find the voltage across ZRC, and that will be the voltage across the capacitor. So it's now ZRC over XL plus ZRC multiplied by the supply voltage. Voltage divider rule. I hope everyone remembers it. Okay. So what do we get? This is our supply voltage multiplied by ZRC. We got this. Then the XL plus ZRC, you are adding these two, and you are going there, right? Since you are dividing, convert this to polar, comes to this value, then divide as usual. This becomes 10 at an angle of what? At the angle between these two, that's minus 45, minus 45. This is minus 90. Minus 90, you get your minus 180. And therefore, the voltage across the capacitor, in terms of mathematical, becomes 10 root 2 sine 1000 t, which is our omega t, minus 180. Right? That's it. So you realize minus 180 is still the same as plus 180. Right? Go this way, this is 180. Go this way, this is minus 180. So it's still the same point. 180 and minus 180. The total current, supply voltage over total impedance. Now these two are in series, so you just add them XL plus that. The only difference now is that you are not adding them directly. You are taking the J100 plus 50 minus J50, right? Then you are now going at this point, you want to divide, convert this to polar, right? Then do your division, you get your 0.141 at an angle of minus 135 degrees. In time domain, 0.041 root 2 sine of 1000, which is our omega t, minus 135. So you realize that everything is still there, still the same. Current through R becomes VC over R because it's still the same voltage across that divided by R. You get that 0.189 of minus 180 time domain √2 sine omega t plus that. Current through the capacitor becomes VC over XC, this one, because there's still across ZRC. Then do your division. Minus J100 is the same as 100, minus 90 degrees. You get your value. You go to the time domain expression. That marked by value times √2 sine of 1000 t minus 90 degrees. That's your IR, current through R. Right. So, still the same thing. We have 5 cos 200t. Again, we want to find IC, IL, IR. We do the same approach. Can you take a snapshot of that diagram and then try to do it as a homework or an assignment? And just test to see if you know how to deal with these things. You want to find this, you want to find that, you want to find that. Okay, let's take a snapshot. Okay, let me remove my lines so that they don't disturb what you are taking a pic of that. But just as a guide, you can see that these are all in parallel. So the voltage is still 5 cos 200t across each one of them. So you don't need to calculate the total current. You just say voltage over impedance, voltage over impedance, voltage over impedance. You get your values. Okay. So this should be 5 over √2. Okay, because this is just 5, there's no √2, so this is 5 over √2. Okay, then this becomes a J50, this is the omega, remember, J200, resistance remains like that. Then, okay, still have the same problem, should go over √2. Then we do our usual division. Another example, take a snapshot of those two. In fact, the actual question is here. This one is now almost like a solution. This two should be 100 over √2 again. That was a mistake because this becomes the RMS and that becomes VM. Again, take a snapshot of that and do it as in homework. Okay, it's for your practice. You don't have to submit it. It's for your own practice. Just in case people will start running around and say there's an assignment, there's an assignment. It's for your own practice. I want you to practice this and to understand it. Okay? Practice and understand. That's all I want from you. Take a snapshot to your calculations. Find the current here and the current in this loop, and also the current in that resistor. And any other thing that you might want to calculate for that circuit. Okay? I think we are good on that. Then another example, calculate the total current supplied by the source and hence the current through the capacitor. Okay? That is the question. I think I had not given the question there. So calculate the total current supplied by the source and hence the current through the capacitor. And hence the current through the capacitor. That is what we want you to calculate. So let's do that, and then we can discuss later to see if there are any issues where you think you might need any help. Because the analysis, like I said, remains the same. Just remember that you are dealing with complex numbers. Nothing more to worry about in those calculations. Thank you for your time. This is the end of our lecture on AC circuit analysis. So we just tried the series circuits, parallel circuits, and series parallel networks. Everything that you did in DC is very applicable and will give you accurate results. So the reason why I gave you that kind of homework is so that you can be able to practice, because all you need is to practice on that. All you need is to practice on that, because that's the only way you can master the concepts. Okay.